All right, so I want to think about some sort of a space curve with you. Here we go. And I want to think about, maybe we're going to start here, and we want to find the arc length from here, maybe out to right there. And then someone else needs the arc length out to here, so we're going to go from there to there, and then from there to there, and maybe someone else wants to go from here. And the way it stands, you'd have to do the integration again and again and again, but at some point you realize, okay, it's the same integral, all we're changing is the bounds. And so that introduces us to the arc length function. And we define it like this: S of t is the length from whatever starting point A, so starting here, out to whatever, integrate out to whatever t that you want, right? Pick your favorite t. And we need to not use a t here to avoid variable confusion. We did this back in Calc 1, so we just switch variables and we put a u. Because when you pick your t, you're not wanting to pick this and this. You're just wanting to say from a to whatever t value you pick, a to 1 or a to 2 or a to 3 or so on and so forth. So that's the change in variables. We're going to need this observation later, so we might as well make it now. The fundamental theorem of calculus tells us that S prime, whoops, that is not what I want. I've got it set on huge ink. Let's erase that. It tells us that S prime of t is just, well, it's just this guy, and you can plug in t, so it's just the length of r prime of t. And so we'll want to make sure that we're aware of that later on. So I thought what we'd do is we would work out an example, and I want to show you one other little twist we can add, and then we'll pop the whole thing in Mathematica and have a look at it. So here's our example. This is the same curve that we did back in 10.7, and I want to find the arc length function. So real quick, to say it one more time, this function S of t, when you say like S of 1, that spits out the arc length from whatever A out to 1 is, and so on and so forth. So, okay, let's switch back to black. So I want to start at t equals 0. I want to go in the direction of t increasing. That all needs to be specified. And so I'm going to begin to write it down. So S of t, well, this is the integral from 0 to t of the length of r prime of u du. Okay, no problem. And so I say, well, so this is the integral from 0 to t of the length of, well, actually, I'm taking the length, so let's do it. Square root of, cosine is minus sine squared is sine squared t, derivative of sine is cosine, so cosine squared t plus 1 dt. And wow, like last time, this works out to just the integral of 0 to t of root 2 dt, so we're going to get root 2t. Now, obviously, you can get some more interesting type integrals. In fact, anything you saw in Calc 2 can come into the game here, but typically they're not too bad. And so the point is that S of t is precisely root 2 times t. And so you want to know the length of this spiral. Remember, this is a spiral. You want to know the length from 0 to 2 pi. Well, it's going to be 2, just plug it in, right? 2 pi times root 2, so on and so forth. Now, I want to say this, and I'll do it here with you in the notes, but then I want to switch to Mathematica and see it as well. We can actually reparameterize with respect to arc length. And let me show you what I'm talking about. I'm going to go back up to my huge curve. And right now, let's say that we pick a random t value. Let's switch colors. We'll call this t equals, I don't know, maybe 3.5. Put you there. And so we can compute the arc length from 0 out to 3.5. And that's fine. We can do that. But what if we had a function that said, okay, if you go out 1, you're here, and if you go out 2, you're there, and if you go out 2.5, you're back here. So, in other words, the function is parameterized by length. So when you say r of 2, for example, you know that you're sitting a distance 2 away from the starting point on the curve. That's really handy in a lot of situations. And so let me show you how we can do that. Let me scroll down here. So we can reparameterize r of t with respect to arc length as follows. Let me actually slide this up, kind of getting behind here a little bit. We can reparameterize r of t with respect to arc length as follows. So instead of thinking of this as S of t, I'm just going to call it S for arc length. S is root 2t. I'm going to solve this thing for t. So t is now s over root 2. And so now when I think about r of t, I can plug in what t is. T is s over root 2. And so this is going to be r of s over root 2, which is going to be, let's actually write it down. This is going to be, well, the cosine of, instead of t, s over root 2, sine of s over root 2, and then s over root 2 like that. Okay, and so this actually parameterizes our curve with respect to arc length. And so let me switch the screen to Mathematica, and I can show you how this is useful. All right, so I've got our space curve parameterized, and the top bar is what you get when you plug in different t values. And it just takes you out to different points, and as t increases, you ride along the space curve. That's all fine and dandy. But what I want to show you is B is representing the parameterization with respect to arc length. And here, as you increase the arc length, what I want you to realize is whatever you plug in, if you plug in 2, you know the point that you get out is a distance 2 away from the starting point. And so if I plug in the same value into the first parameterization and the second parameterization, let's say that I plug in 3. Well, the first one, you're just at t equals 3, which is up here. It's random. The second, when you parameterize with respect to arc length and you plug in t equals 3, you know you're exactly 3 away from the starting point. So it's really convenient to parameterize with respect to arc length. Whatever s value got me to this point is the distance, the arc length on this curve that I am away from the starting point. So that's how it works.